The electromagnetic theory and interference course. In this session, let us see about the magnetic flux density through which we will arrive the fourth Maxwell equation. Already we saw about electric flux density, right? So here the magnetic flux density B is similar to my electric flux density D vector. We know that D is equal to epsilon naught E in free space. Similarly, the magnetic flux density B is related to the magnetic field intensity H by B equal to mu naught into H, where mu naught is a constant here and it is going to be the permeability of free space, and its value is 4 pi into 10 power minus 7 Henry per meter. So once the magnetic flux density is known, we can find the magnetic flux that is flowing through a surface. So the flux notation is same as electric flux psi, that is equal to surface integral of magnetic flux density. What is the unit of magnetic flux? It is Weber, and magnetic flux density is Weber per meter square or Tesla. So let us understand how the magnetic flux lines are present due to a straight current carrying wire. So this is a straight current carrying wire. The magnetic flux lines are enclosing it. Okay, and these lines will be closed. Each of the flux lines is closed and doesn't have any beginning or end. Okay, and doesn't cross each other also. The magnetic flux lines doesn't cross each other. So now let us understand the final Maxwell equation. For that we consider the flux leaving a closed surface. Okay, due to the isolated charge, we can see here the flux is equal to the charge enclosed within the surface, right? It is a positive charge. So the flux lines will orient from the positive charge towards the infinity. So flux psi is equal to closed surface integral of d dot ds, that is equal to the charge enclosed, that is from for the electrostatic field. So it is possible to have a isolated electric charge. So we can have isolated charge also, but electric flux lines are not necessarily here. It is closed always. Okay, but unlike this, my magnetic flux lines always close upon themselves. So if you see, it is closing themselves from starting from the north pole. It is going and ending at the south pole. Along this closed surface, if I see, the flux is going to be zero. So it is not possible to have an isolated magnetic poles. So isolated magnetic charge doesn't exist in practicals. Okay. So the closed surface integral of v dot ds, that is equal to flux we saw, right? That is going to be zero. Okay. Around the closed surface, if you see, it is zero. General case, I can write open surface, it is equal to flux, but closed surface, it is going to be zero. So this can be understood from this example. If I successively divide by magnet into pieces, again north and south pole will come, and I can't separate the magnetic poles. Okay. So the above equation that we saw here, so the magnetic, the total flux through a closed surface and a magnetic field is zero, right? So this is called the law of conservation of magnetic flux, or Gauss's law for magnetostatic field. Whereas in Gauss's law for electrostatic field, we know that along the closed surface, if we find the surface integral of electric flux density, is going to be charge enclosed. Okay. Even though my magnetic flux is conserved, my magnetostatic field is not conserved. That we saw in the previous session, right? Del cross H is equal to J we have found. Okay. And if I apply the divergence theorem to above expression, so it relates surface integral of closed surface integral of a vector to the volume integral of the divergence of same vector. So if we compare the divergence of the magnetic flux density is going to be zero. This is my fourth Maxwell equation. We know that magnetostatic field have no sources or sinks, and it is always this field lines are always continuous. Thank you everyone. Let us meet in the next session.